Hello, my name is Leandro. I am a pilot in the Brazilian Air Force who worked for 7 years fulfilling missions in the Amazon Rainforest. In the last years of my professional life, I had the opportunity to start a postgraduate program in computer engineering. In this video, I would like to share one of the projects I developed here. It's basically a way to detect targets located in the Amazon rainforest, and which are used for illegal activities such as mining and drug trafficking. Clandestine airstrips. In the past, I used it to carry out missions by recognizing these targets visually. Still, my computing knowledge allows me to do this remotely and efficiently. In this video, I will share with you the steps I took to generate my own dataset and train a YOLOv8 model to detect these runways. The Brazilian Amazon, covering over 5 million square kilometers, is a vast and diverse territory, rich in biodiversity and natural resources. However, this region faces a series of challenges related to illicit practices. A growing concern is the presence of unauthorized airstrips, which are frequently used for illegal activities such as mining and drug trafficking. Moreover, they are difficult to detect and monitor using visible spectrum satellite images, due to the dense and constant cloud cover in the Amazon during certain periods of the year. This high prevalence of cloud cover complicates the detection of illicit activities and the assessment of environmental changes. In this context, synthetic aperture radar is a tool capable of overcoming such challenges by providing high-resolution images of terrestrial and maritime surfaces, irrespective of weather conditions and the sunlight. The effectiveness of SAR radars in detecting targets and environmental changes, even in extensive areas and under various atmospheric conditions, is documented and recognized. The figure presents a SAR image obtained even under adverse weather conditions. However, the complexity of these images can pose a significant challenge for human interpretation. Given this complexity, integrating computational resources such as artificial intelligence has proven to be a solution for extracting information from them. With its capabilities for deep learning and processing large volumes of data, AI provides support to expedite decision-making using these images. Some results presented in studies involving the automatic detection of targets in radar images point to a promising scenario for the use of artificial intelligence for this purpose. Given the negative impacts caused by clandestine tracks in the Amazon, the advantage of using SAR images, the promising results from AI studies with the YOLO model, and the lack of research on detecting these tracks using SAR, this study aims to evaluate the performance of the YOLOv8 model in detecting such targets. Initially, the position of the airstrips was verified in Map Biomas, a multi-stakeholder collaboration involving academia, technology firms, and NGOs in Brazil. The collaboration focused on mapping and monitoring changes in land use and cover nationwide, using advanced remote sensing and geospatial analysis. The project provides geographic data, including locations of authorized and unauthorized landing strips, assisting in logistical planning and field studies in the Amazon. Here, we can see the location of some airstrips mapped by the project. The list of geographical coordinates expressed in decimal degrees of longitude and latitude was compiled to identify locations with unauthorized airstrips. This list was incorporated into a Python script executed in the Google Colab environment. The initial script procedure involved installing and configuring the Google Earth Engine API, providing full access to the platform's data manipulation and geospatial analysis capabilities. For each location identified as containing an airstrip, an image slice was taken, covering an area of 4 km² in 200 by 200 pixel images from Sentinel-1 satellite, corresponding to the year of 2023. The images were obtained in the interferometric wild mode and vertical-vertical polarization. Subsequently, the selected images were exported for storage in the cloud, followed by downloading for processing in a local environment. To prepare the images for analysis using the YOLOv8 neural network, the original data was converted to the PNG format using 8-bit integers. The images were labeled in the standard required by the YOLOv8, aided by the use of high-resolution images from planet constellation, corresponding to the exact dates of the SAR images. This approach was adopted due to the need for accurate identification of the airstrips, as the visual characteristics of these structures often appear indiscernible in radar images. Moreover, the targets are volatile. The airstrips can be temporary, with vegetation quickly covering previously deforested areas, or they can emerge suddenly due to illicit activities such as mining, requiring checks in visible spectrum images for their existence to ensure correct labeling. At the end of the image acquisition process, 1,040 airstrips were obtained. The targets were randomly divided as follows: 646 images for training, 277 for validation, and 117 for generalization testing. The pre-trained YOLOv8X large model chosen for this study has the most robust architecture in the series, with 68.2 million parameters, making it particularly suitable for scenarios that require high precision and superior performance. The model was trained using a GPU with 16 GB of memory to handle large datasets and high computational complexity. Did you like this video? Don't forget to leave a like and subscribe. Don't miss part 2 of this study, where I will show the performance of the YOLOv8 model in detecting these targets. See you!